Hello everyone, myself Swaroop and today I am representing the analytical instrument bomb calorimeter. So let's see the content in the presentation. First is the motive, second is the introduction, then principle, structure and components, operating procedure, calibration, applications, limitations, case study and example. So by motive of choosing the topic is as we are engineering students, not only chemical but also mechanical and environmental engineering students, we learn about reactions, their energy required, their mechanism, their efficiency, and so on. For reactions to be proceed, the main requirement is energy content of the substance that is the heat of combustion, also known as calorific value. As the world move towards the environmental sustainability, we should know about the use of bomb calorimeter for knowing the calorific content of any material. Before introducing the bomb calorimeter, let's know about the calorimeter. The calorimetry is a technique used to measure the heat released or absorbed during chemical reactions or physical changes. It provides valuable insights into reaction dynamics, thermodynamic stability, and energy efficiency. Now, the bomb calorimeter. The bomb calorimeter is used to measure the heat of combustion or the energy released when a sample burns or calorific content of a material. This is the measurement which is essential in industries that rely on understanding energy density, such as food science for caloric content, like also in nutrition, diet, and the energy sector for fuel assessment. The bomb calorimeter has very high significance due to its application in various industries. Like in food industry, it helps determine the caloric content of food items. In the energy sector, it aids in assessing the combustion properties of fuels to improve efficiency. Let's talk about the principle. There are two principles involved in bomb calorimetry. The first is the first law of thermodynamics, which is the energy neither can be created nor can be destroyed. So the bomb calorimeter functions based on the principle that energy can neither be created nor destroyed and only transferred one form of energy to another. When a sample combusts, the chemical energy is converted into thermal energy absorbed by the surrounding water. Principle 2, the heat of combustion. This is the total amount of energy released when a substance combusts completely in oxygen. In a bomb calorimeter, this energy is trapped within the system, leading to an increase in temperature, which can be precisely measured. Structure and components of bomb calorimeter. Here you can see the image. So the outside insulated container is known as calorimetric box, and this inside container is known as bomb. This is the area where sample is placed. This is the igniting coil. This is the ignition box. This is the stirrer. Here in the surrounding, we have taken the water. This is the thermometer, and inside the bomb there is oxygen. So, talking about the bomb or the combustion chamber, it is made of robust, it is heat resistant stainless steel. The bomb chamber holds the sample under high pressure oxygen. The robust design prevents any leaks, maintaining high accuracy in energy measurement. This is the bomb. Oxygen supply, pure oxygen is pumped into the chamber to ensure complete combustion. The amount of oxygen is precisely controlled to ensure consistent combustion conditions. Inside this bomb, there is oxygen. Water jacket or water bath. It surrounds the bomb chamber and absorbs the heat release. By monitoring the change in water temperature, we can calculate the heat of combustion accurately. Here is the water. Temperature sensors or thermometer. Highly sensitive sensors measure the change in temperature within the water bath to a high degree of precision. Steering mechanism. It ensures that the water temperature is uniform, as uneven temperature distribution could lead to errors in calculating heat. This is the mechanical steerer. Ignition system. This typically consists of an electrical wire or fuse that ignites the sample inside the bomb chamber. An electric spark initiates the combustion process, and the energy input from the ignition is accounted for in calculations. Uh, then let's see the operating procedure. So continue with this diagram. So when we ignite a sample, usually 1 or 2 gram, it will be combusted, and so the temperature in this bomb will increase, but it is trapped, so it is absorbed by the surrounding water, and the temperature of the water will increase. Due to this mechanical stirrer, it will be uniformly increase the temperature. So the coil of this temperature sensor, it will calculate the temperature. We have to record the temperature readings. Sample preparation. The sample is carefully wetted and placed in crucible within the prom. Accurate wetting is essential for reliable results, as even minor differences can impact the final heat of combustion. Loading the bomb. Once loaded, the bomb is filled with oxygen under pressure. This ensures that the sample burns completely when ignited and maximizing energy release for measurement. Sealing and immersion. The sealed bomb is placed in the water bath, which is carefully monitored for temperature changes. Ignition. The sample is ignited by an electric spark, causing rapid combustion. The heat release ra- raises the water bath temperature. Here is the sample which is ignited. Temperature monitoring. The temperature rise in the water bath is monitored closely to capture the peak value from which calculations will be made. Calculation using the formula Q is equal to C into delta T, where Q is the total heat absorbed, C is the calorimeter's heat capacity, and delta T is the temperature change. The heat of combustion is calculated. Data analysis. Results are standardized, often as energy per gram or per mole, allowing comparisons across different samples or studies. Let's see a small video on the working. The sample is ignited, so the temperature of the surrounding water is increased. Due to the mechanical stirrer, it will uniformly increase. Slowly, the temperature will increase. We should note the temperature readings. Calibration. So, as here you can see that this is the insulated container. It has some heat resistance, so we have to calibrate for minimizing the error. Calibration process. The calorimeter must be calibrated using a substance with a known heat of combustion, such as benzoic acid, to determine the calorimeter's heat capacity. Importance of calibration. Calibration ensures that any heat absorbed by the calorimeter itself, not just the water but, is accounted for. This heat capacity is essential to accurate energy measurements. Using calibration results, once calibrated, the calorimeter's heat capacity value is used in future measurements, providing an accurate basis for determining the heat of combustion for samples. Application. Now let's see the applications. Energy and fuel industry. The bomb calorimeter helps assess fuel efficiency by measuring the energy content of different fuels. This data helps optimize fuel use and guide the development of alternative energy sources. In food science and nutrition, used to measure the caloric content of food, bomb calorimetry provides information essential for nutritional labeling and dietary guidelines. Material science, analysis of combustion properties of various materials such as plastic and textile is crucial for safety evaluations such as flammability and risk. This is the interesting one. The last, environmental studies. Analyzing biomass or waste products as energy source is another application. It helps assess the potential of renewable energy sources, making it valuable for sustainable energy research. This means the waste the biomass waste which we generate, it is efficient or not for producing energy. We can calculate it using bomb calorimetry. We will take one case study on this afterwards. Let's see the limitations. Despite having many applications and high accuracy, the bomb calorimeter have following limitations. High initial cost and maintenance. Bomb calorimeters are expensive to purchase due to their precise design, materials, and advanced sensors. Also, regular maintenance is required to ensure accuracy. Limited to combustion reactions, the bomb calorimeter is designed only for reactions involving combustion. It cannot measure the heat changes of non-combustive reactions like phase transitions and reactions in aqueous solution. Time-consuming process: setting up the calorimeter, preparing preparing the sample, and filling the chamber with oxygen require meticulous attention, making the process relatively slow. Limited to small sample sizes, bomb calorimeters can only handle small samples, typically 1 to 2 grams. This limitation may not reflect the behavior of large quantities in real world application, especially for industrial fuels. Now, let's see the case study: biofuel versus gasoline. Biofuels such as biodiesel and ethanol, also biofuels produced from the biomass, are gaining attention as sustainable alternatives to fossil fuel. However, their energy content is often lower than that of traditional fuels like gasoline. Bomb calorimetry is used to measure and compare the heat of combustion of these fuels, providing insights into their efficiency and potential for large scale adaptation. Taking a fixed mass of biodiesel and gasoline was weighted and placed in separate crucibles. Let's take 1 kg of biodiesel and gasoline. Now using the formula Q is equal to C cross delta T, where Q is the total heat absorbed, C is the calorimeter heat capacity, and delta T is the temperature change. The heat of combustion is calculated. The heat of combustion, that is the calorific value. Results: the calorific value of gasoline is 44 megajoule for 1 kg and for biodiesel 38 megajoule. So we can conclude from this result that while biodiesel is a viable renewable energy resource, it has a slightly lower energy output compared to gasoline for same mass. However, biodiesel's environmental benefits such as reduced greenhouse gases emission and biodegradability may outweigh its lower calorific value, making it a strong candidate for sustainable energy. There is another example. The food industry uses bomb calorimeter to determine the caloric content of various food items. We will measure the caloric content sample of 2 gram and compare the measured value to the value provided on its packaging. We have seen many times on the these packets on the backside there is the energy energy content value given, and many nutrition value also given. A 2 gram of sample of crushed potato chips is weighted and placed in combustion crucible. The bomb chamber is filled with oxygen and the sample was ignited. Heat released during the combustion reached the temperature of the surrounding water. Under the water's temperature increase, The total energy released by the samples was calculated in kilojoules. So we get the results. The measured value of the bomb calorimeter was 520 calories per 100 gram, and on the package it was labeled as 500 calories per 100 grams. It is showing a close correlation with the tested value, so it is ac- highly accurate. Thank you for listening.